All right, welcome back. Today I'm going to be showing you some data analysis and a couple of things before we get to the analysis itself. So the first is about the libraries. I'm not sure if I mentioned to you before, but some of the libraries here that you're going to call, or in this case I'm calling them, you might have to install them to be able to use. So if you remember from one of the first videos that I showed you, I think I showed you how to install a new library and then how to call the library. After you have them installed, you don't have to call them again anymore, and you can just run them, or you can just call them and they're going to be available for you use. So I already run those libraries. The second thing I want is to import my data set. And in this case, I have 3 data sets. I'm not going to use them all. I'm having examples how to import your data sets. And another thing that I want to show you is how to summarize this data set. So for your analysis for the lab, you're going to need to summarize your data set because we want to do a one-way ANOVA test. So analysis of variance with one factor. So the factor that you selected or your independent variable, or basically your treatment. So I don't want you to include more than one factor, for example, weeks, or the age of birds, or different periods, or you could even include more than one treatment. So that will become a factorial experiment. Therefore, we're gonna have to summarize our data. So in this example here, I want to summarize this data. So I want to get the average daily feed intake for the rearing phase for each bird from 0 to 21 weeks of age. So that would be the rearing phase. So I will start, I'm going to use data 2. And data 2 has a lot of columns, and you can see a lot of entries here. So it's almost 180,000 entries. So this data is summarized by day. So you have every day the feed intake of birds. So there's 0, no feed intake. But basically you have the feed intake for every day of all these birds. And you can see a lot of columns. I don't want that many columns. So for the first line of coding right here, I'm going to remove most of the columns. And I'm going to keep only the bird identification, the study number. Remember, we have more than one study, and the age of those birds. So I want the weeks, I don't want the days, the treatment number, and the response variable I'm interested in, which is the average daily feed intake. And this would be data 3. So now you can see that this data is a lot cleaner than the data 2. Additionally, in data 3, I have some NA, so some non-applicable where there's data missing, and I want to remove that because when I summarize this later, that will mess up with my readings in R. So I'm going to remove that, and I overwrote data 3, and you can actually see the NA is not present anymore. So right here, I have the line of coding, or the lines of coding for this summary of the data. I'm just going to go over this. So data 3 is the data that I'm actually extracting or making the new data set. And in this case, because I only want the feed intake from 0 to 21 weeks of age, I identify that I'm going to select this data based on week, and the week that I want included is 0 to 21 weeks of age. And I'm going to group this by RFID because I want information by bird, so the RFID identification. And the treatment number here would be because I need the treatment number to be able to analyze this data later. And I'm going to summarize. I'm going to add the average, so basically the mean of average daily feed intake, or daily feed intake from 0 to 21 weeks of age. Actually don't need this line of code here. And I'm going to rename this this variable right here, so the mean average daily feed intake, I'm going to call it mean. Okay, so I create new data set. Let's have a look. So now you can see I have RFID, treatment number, and the mean. So this is the average, basically the average intake for each individual bird from 0 to 21 weeks of age. And then if I want to analyze this data, I would follow it with the analysis. So this data will be ready for to analyze. Okay, so I want to show you an example, and this example will be lean percentage. So as I mentioned, I want to use specific times. So for lean percentage, so let's have a look at the data here that I have for our carcass composition. So you can see there's several weeks starting at week 4, going to week 8. If we keep going down, we're going to see week 12, and so on. And if I'm not mistaken, we have up to week 28 in this case right here. Because we want to do one-way analysis of variance, so only one independent variable, we don't want to include age, I'm going to have to select the age that I want. I could also summarize the average of the carcass fat or carcass lean in this case that I'm interested, or any other variable, response variable that I'm interested. I could summarize and get an average from a certain period, as I've done for the average daily feed intake. But for the carcass composition, the average over a bird lifetime doesn't really matters to me. So for example, one important time point is just before the photostimulation. Let's say at 20, I have at 22 weeks of age here, or at 20 weeks of age, because that will gonna tell me more what the state of bird just before an important time would be the photostimulation, or just before the sexual maturity of those birds. So in this case, I'm gonna select, or I'm gonna prepare this data based on one study. So I'm gonna make sure select only study number 1. So I'm gonna do for the experiment 1 here. And because I only want the I2 level as a main factor in this analysis, I'm gonna select the standard G2 to G1. So if you remember from the class, this trial was actually a factorial trial. So we have different levels of G2 to G1 and different levels of I2. And you probably can remember, or you can check those acronyms later. So I'm only interested on the 0 or the standard in this case for the early growth of these birds. And then I'm interested in the data from 22 weeks of age. So I'm gonna run this line of code, and I have the data lean ready here. So here you can see that I have only 24 entries, and they're all from week 22. They all from study number 1. And if you check the treatments, they all from the standard G2 to G1. So the standard will be 0, which is no shift in gain. And then we have our different treatments here. All right, so to do the ANOVA test, so the analysis of variance, I have 2 codings that you can do in different ways. I'm just gonna run the second one, but you are aware there's different ways to run this code. So the second, basically, in the second analysis of variance, it gives you the table of analysis of variance. I'm not gonna go, or the ANOVA table, I'm not gonna go a lot of details on this because this is not a statistical course, but the number that you're gonna look for is the p-value. So the p-value here was less than 0.05. And the p-value one is, so as more or less an arbitrary number, the 0.05 is used usually to test or to give you the p-value to test your hypothesis. So the p-value means the probability of equality or the probability that your null hypothesis is true. So in this case, the p-value is low, so it's lower than 0.05, which is usually the number that we set. So that means that we reject our null hypothesis, which would be the quality between the treatments, and then those treatments are different. But of course, now we're going to see exactly what's the difference between our treatments. So we can run the means. You're going to give you the means in this coding here. Again, I have two lines of codes here for the same function. I'm just going to run one of them. And now you can see the means for each treatment, the standard error. The standard error basically gives you the accuracy of a sample of a mean of a sample mean, basically. And you actually use the standard deviation to calculate the standard error. Not going a lot of details, but usually when you present data set, it's nice to have an estimate of the error on your mean, and that's why it's important to add the standard error. So you have to remember that when you provide your results, you have to, or it's important to provide some estimate of error of your population, of your sample in this case, and then the standard error will be a standard measurement that is usually reported. Okay, so if you remember seeing any data being reported, you sometimes would see some letters. But in this case, to show the letters or to actually show which treatment is different from which, so you can see you have a difference and the numbers here, but we don't exactly know which treatment is different from which treatment. So to do that, we have the CLD option in R. And then with the CLD option, you basically use the 2K method, which is a post hoc test to exactly check which treatment is different from which treatment after analysis of variance. And then in this case here, I already added the letters for us in the graph, or sorry, already added the letter for us in this table. So you can see when you actually compare the treatment 15, 17, and 19, you can see that they are not different because they all have the letter A. But when you start seeing treatment 21, 23, and 22, those three treatments are different from treatment 15. For example, treatment 21 and 17 are still the same. So both of them are statistically the same, considered the same. They both have a letter B, but treatment 23 compared to 17 are different from each other. So this is just an example. So what you could do, you could actually export this to a CSV file. And then if you open your CSV, or if you open the local where you export that, you can actually open this CSV file. And then you're able to see the mean, the standard error here, and you actually have the grouping too. So you could make a graph directly from the Excel based on this data. However, I suggest you to use R to do your graph because you're going to spend some time invested in that to do the graph, but you probably would save any extra time if you have to make adjustments. And usually on Excel, you might not have as many options as you have on R. So I'll be showing you how to do that graphing in the next video. So for the data analysis part, that's basically what I have. I have some additional resources in this file for analysis of non-parametric data sets. because when you use, for example, use binary variables or variables that are a score that we actually have in our trials, so a feathering score, for example, or a breast muscle score, you'd want to use, or you might have to use, some non-parametric analysis. But this is just as additional resources, because for the data sets that we have, and even if you don't have parametric data, I would recommend you to use this analysis here, so you don't get into a lot of details regarding the statistics, and I'll leave that for a statistical course, and that will explain to you why would be the best for non-parametric data to use some non-parametric analysis. I also have some two-way ANOVA resources here if you're interested in learning when you include, for example, age and the specific treatment that you're interested. So you have two factors in this case. And I also have some examples for linear mixed models. And this would be mostly for Dr. Zuidhoff. I know he's interested in R, so he might want to look for this when doing his analysis in R. Dr. Zuidhoff and myself, we like to use SAS, or actually we've been using SAS for most of our life. And SAS is pretty fun, but learning a little bit of a new program for statistical analysis and data processing is interesting.